Hey, Cassandra. Oh, class over is still up right here. How are we doing? I think we've got good internet today. I've totally jinxed it now. We're in trouble. Brian said the internet's working. The internet's going to fail us now. But if you have questions, let me know. What questions do people have? We can start up. People are saying office hours are a lot of help. I got a lot of that great feedback today during class. Maybe it's because I'm using OBS as administrator mode. I don't know. Did the cord? Yes, Leo. Totally redid. I've got a ton of them. Here, wait, watch this. You ready, Leo? Be right back. Watch this. 2 seconds, Leo. Okay, here we go. So I have rewired. I only needed like 3 of them, I think, but I have rewired everything. So it's all they're over there. I need to put them up in the storage. But brand new Ethernet cords, Cat 6, the ones Leo suggested to me. Can you do chapter 13? Yeah, homework question 3. Of course. Yeah, let's do that here in a moment. You bet. Thank you, Leo. If things are working well, it is thanks to Leo. So, Leo, let's give some 500 points. And Christian, great question. This is going to be a tough one. Ooh, tough questions. Chapter 13, homework question 3. That's some good stuff. Oh, gonna fall asleep. Need coffee cup number 3. Gonna fall asleep. Need coffee cup number 3. Coffee. I sadly have a caffeine addiction. I think I got sunburnt a little bit yesterday. A little sunburn yesterday, going out in the sun, getting some coffee. Got everything rewired. Thank you, Leo, for that suggestion. I hope it works too. We haven't had an issue yet, Leo. I'm also running OBS in administrator mode, so that could help too. I think you want sampling distribution of the sample mean. Ooh. When does this one do? My gosh. 2 seconds. I'm going to probably change some due dates. That's due on the 11th. This is due on the 6th. And that's due on the 11th. Let's put this... Man, it's just so tough. If I put something to do Friday, no one's going to do it. If I put something to do on Friday, no one's going to do it. Nobody's going to do the assignment. Friday due dates are a horrible idea. I would put it to Friday, but I know from history that you put something due on Friday, it's not happening. So, trying to remember how to change dates and assignment status. So we'll get started on this here. Do you have the start of the question? I think there are multiple choice questions. What is drawn from? Is that the population? I'm overthinking this multiple choice. The sample would be drawn... Well, it could have like sample frame. Did you give OBS as well as a Chrome priority in your network? Maybe. Leo, do you have information on that? Maybe I need to be doing that. But Leo, send me or explain. It might not have the right priorities. Like it might not be using. It might like lower CPU. I don't know why it would be doing it. Like, you know, we might have troubleshot the issue. Thank you, Leo, for all this help right here. I'm updating some settings, and we're going to do Christian's question. Cassandra, if you can expand upon that a little bit right here. We're about to hop into... Yeah, and Leo, thank you so much. Remember, you don't have to do any of this. I appreciate it. There's so many points of failure in I'm going to stream a class on the internet that it's easily could be anything. But good news is we haven't seen any issues yet. So we may have fixed the issue. It may have been just Ethernet cords, because I think I was using the one that came with the router, and they're not going to give you some amazing cord, because I looked and I was like, oh, it was like a 1 foot wire that I had that came with the router. So they probably were just giving me some like Cat 2, you know, really old wire that, you know, is not meant to be super fast, high quality. But you would think, oh, this is the shortest wire possible, so it's going to have less signal loss or whatever. I would think it would have been a good wire, but I had no idea the certification on it. You'd think they'd want you to really like their router and modem, but rewired everything. So it wasn't a bunch of work. There wasn't a lot to rewire. Just unplugging, rehooking in 3 Ethernet cords. So that didn't take, but I don't know, 10 minutes. Took longer for the wires to come in. Took, a day or two for the wires to get here on Amazon. Okay, so we've got the sampling. There we go. Sampling distribution sample questions. Question 3. We'll be covering these notes next class. This is a tougher chapter. Oh, it's the bank loan question. Oh, hey. Yeah, tons of potential issues. It's so crazy. It's a lot of fun. I like it, but you never know. Okay, here we go. 6. Stat Tool 1, Chapter 13, Bank Loans. Let's go jot out some bank loans. Here we go. Okay, so we're on the bank loans question. Now, this is the sampling distribution of the sample proportion. There are some key things we need to know while doing this. Anytime we do a sampling distribution, we need to figure out 2 things first. A lot of questions will walk you through these steps. But what do I mean by a sampling distribution? A sampling distribution is to say, I know the true kind of mean or proportion. Like, let's take this for example. 40% of UT students are in-state. If you go out and talk to students, what percent of students would you expect to find in your sample in-state? So take this example for a question. Take this question for example. We know that 40% of UT is in-state students. You go out and talk to 200 students. What percent of your sample would you expect to be in-state? It's that simple. If you're thinking, is there something more to this? Like, I thought statistics was supposed to be crazy and difficult. A sampling distribution is when you know the truth of a population, which you know up here. We know that 40% is in-state. What percent would you expect in a sample of 200 in percent? You might be thinking a number. Don't worry about the number, because you could figure out how many you would expect. But we know that 40% is in-state. You talk to 200. What percent would you expect to be in-state? So we'll see if anyone answers in the chat right here. But this is a good way to remember. It's like, yeah, Christian, that's all it is. That's 100 points right there. This is all it is. So you're actually doing some of the work for this chapter. What you're actually solving right now is the equation mu p hat equals P. So we have to know our notation here a little bit. Like, this is where it starts to sound a lot more complicated. P is the true proportion. The true proportion is like what percent of UT is actually in state. Does that make sense? Like, P is the truth. There's 40% of UT in state. So then we would say, what would we expect in a sample? So what would we expect in a sample? We'll change the colors. The expected in the sample is right here, expected and percent in a sample. So that's the way that reads, where this is the truth, and that is P right there. So we're saying if we know that 40% are in state, well, then if we take a sample, we'd expect to see around 40%. But there's another quantity we would need to know, and we don't always have, or we need 2 things for a sampling distribution, not just the mean of the distribution. We would also need the what for it. So what is the other quantity we would need to know? Not just the center, but when we talk about things that are normally distributed, we need a mean, and we also need a second quantity for it. What is the second quantity? Because we'd have to know where the center of it is at. So that's the center of it. We need to know the standard deviation. Great answers right there, Christian. So the standard deviation is how far is it going to spread out? And that standard deviation is going to be sigma. So sigma p hat is equal to p times q over n square root. And that's the whole square root. P times q over n square root of the whole thing. P times q over n square root. So then the question becomes, what is q? And we'll see how we solve this here in a second. Q is going to be the complement of the sample proportion. So if P is equal to 40%, in this example, Q is equal to 60%. And then N is the sample size right there. So that's going to be equal to N, which is the sample size. And from here, it's just solving of the problem. So understanding how to take the notation on this and what it's going to be asking you is very important. let's bring this idea over to our question. And thank you so much, Christian. 100 points again. Thank you for following along with this example right here, because it's going to make our lives a lot easier with this question. So let's take, for example, the first question right here. It says the bank believes 12% of people will not pay their loans back on time. They're going to give loans to 400 people. What percent of the 400 would they expect to not pay their loan back on time? So this is expected from the sample. That's how that reads right there. What would they expect in a sample to see for the proportion of people who wouldn't pay back their loans on time? If the bank believes 12% of people won't pay their loans back, they give loans to 400 people. And remember, this is percent or proportion. What percent of the 400 would they expect? There you go. It's that easy for the first one. And then the next one says, what is the standard deviation? And they're abbreviating it SD right here. You could do the sigma, but they call it SD for standard deviation right there. So remember the equation we had just a moment ago. We'll take this question right here, bring it over here to a Word doc. Remember the equation is going to be P times Q over N square root. So we want to take our notation right here and make sure we know what the notation is. This is what the bank believes is true. So that's P. And then Q is the complement, 1 minus P. So it's just whatever adds up to 1 is Q. It's the bank believes this percent will not pay their loans back on time, and the bank believes this percent, 88%, will pay their loans back on time. So now, to solve this, we simply do P times Q over N square root. And so that's going to be... So try to solve this out as I'm writing it down. See if you get the same answer. Good practice, just calculator practice right there. And we go P times Q over N square root. And there it is. There's the standard deviation. Can you do more? Yeah, Warren, feel free. Which one's chapter 12 is it, or the one we were just doing? We can go check it out and do another version. Why not? We'll do that here next. Could you read the question about the adult women in a certain geographical region? You bet. Cassandra will do that one after Warren's question. So that's next on the... Let me write them down, because if I don't, I'll forget. Canvas, content. Is it number 6, Warren? Number 6. And then Statute 1, chapter 13, adult women in region. Okay, cool. And so there we go. There's P times Q over N square root. And that's the standard deviation for us. So the standard deviation goes right there. Delete down to 3 decimals. Watch out on the round at the ending. There we go. Check answer. We're good. So once you have this, and this is what the problem doesn't say to do, but you should do it. Good job. Number 6. What we should do is we should draw it out. Now, the easiest way to draw this out is to go to the David M. Lane. You won't have access to this on the test. So on the test, you would go here and you would do the following. On the test, you would know that the mean of the distribution is normally distributed with a mean of 12 and a standard deviation of 0.016. Those are numbers we just got for the mean standard deviation. So you'd go right here, draw your curve on your sheet of paper, put 12% at the center, and then go down, down, down 3 standard deviations, and go up, up, up 3 standard deviations. And then right here, you would have 0.136. And below these, I'd start putting my z-scores to help me with the problem. Now, the reason I'm not going to do the rest of this is because right now, as we're working on this, we have the David M. Lane. The David M. Lane is going to be basically my way of solving it a lot quicker when I'm not working a test question. And remember that number I just found right here? And for some reason, it doesn't always put the third number. It's an error I've seen with the David M. Lane. But look at the numbers I've started to write, and you will see the remaining numbers mostly right there. So once again, we don't have to use the David M. Lane, but it's going to help us draw it out. We should understand, though, how to draw it without the David M. Lane, as I was doing previously, putting the mean at the center and using the standard deviation as a unit of length to go up and down. And you can see it does the work for you right here, just up the standard deviations. We could tell what the next number is, so we could put it here. We could take and add this to 0.152. And here's the next number on the curve if it had shown that next standard deviation. So we could pretend it has this next number right here if we really need it. So we understand what it's showing us. Now, what does this mean? So, Christian, this is where people usually get confused. What am I seeing right here? Imagine you're throwing a dart at this board. This is a dartboard for you. And I say you hit the dartboard. What is the most likely thing to hit on this dartboard? If I say you hit the dartboard, you threw a dart, boop. And where was one of the more likely spots to hit on the dartboard? Because we're trying to understand, what does this graphic mean? What is it telling us? Like, what have we created? Probably close to that, right? It's the center of the board, right? This is the center of the board, so probably a likely spot to hit. So if you give out loans to 400 people, a very likely amount to not pay their loans back on time would be 12%. Does that make sense? Now, down here on the far side of the board, which is a smaller error, remember, we're saying we hit the board somewhere. It's a very important part of this analogy. Down here is a very unlikely spot to hit. Does that make sense? Because there's not much area below it. So that might be around the probability of 7.5% is very unlikely to see. So if you gave out loans to 400 people, it'd be very unlikely that around 7.5% of people would pay back their loans on time or less. Does that make sense to say like that? Like if I gave loans out to 400 people, it would be very unlikely that 7.5% of them or less would pay back their loans not on time, because it's the percent that don't pay it back on time. And so now the question wants us to ask, let's see what the question asks. It says, there's that. Oh, the conditions. Condition 1, randomization, which means we randomly selected these people. Condition 2, it's less than 10% of people who we're giving loans to, the less than 10% condition. And condition 3, we have at least 10 successes, at least 10 failures, found by NPNQ. Conditions, we'll probably see a lot of those. Just have them memorized. We'll practice them a lot. And we would do right here, NP, there's 48. NQ, there's more than, there's 352. We have at least 10 successes, at least 10 failures. So with reasonable assumptions, they are met. I do conditions in a lot of questions, so you'll see me do a lot of those. So now this is the big question right here. What is the probability that over 15% of these clients, that over 15% will not make loan payments back on time? And I'd like for you to just look at this visually. Wow, and it's almost right here. This is almost a z-score of what, Christian? This is almost a good test question. 15% is almost a z-score of what? 15% is almost a z-score of what? 15% is almost a z-score of what? 2. Exactly. What's really interesting about this is it would land right about here. And you could z-score it. It's probably going to have a z-score of like 1.96 almost. So, Christian, I want you to take a guess at this area. How much area do you think that is? Now, we're going to use the David M. Lane in a moment to solve this, but this is what it should look like visually. We understand what it should look like visually, but I want you to just take one guess at the amount of area you think this is. So do remember, and this is where a test question could come into play right here. So we do like to try to teach to the test. If we went out to 2 standard deviations, it'd be something like that. 2.5 or so, right? Good guess. Very close to 2.5, and that's why it'd be a decent test question. It says to 3 decimals, so I'm going to go I'm going to go that, check answer, and we got it. I wonder if, would it have accepted? I should have entered in your answer. Very close. As a decimal, about 2.5. I went a little bit larger because we were a little bit further in. And to do this on the David M. Lane, you would go right here and just go above. And the exact answer is this. So we should have just guessed 3%. 3% would have been really close. And look at our drawing compared to it. If you compare our drawing to what they show, look at how close we made the drawing. I wish I could, maybe I need to zoom this out a little bit more. But you can see our drawing is virtually identical to it. I'll disappear so you can see it. Oops, didn't want to full screen. But our drawing looks a lot like what they have going on right there with it. So you want to be able to draw this out and be able to graph it and understand what you're seeing. And that's got it. So Christian, did you get the question right? How'd it go? Good work on this, and hopefully you understand what it's showing you. And then you can make educated guesses on the percentages by knowing your normal curve, your 68, 95, 99.7 empirical rule. And that's why the knowledge kind of builds upon itself with additional knowledge. Well, we're going to head back here to the main screen. We'll come back and we're going to do some Canvas content and then head back here. Okay. I feel like maybe I hear the sound later. I don't know. Maybe I turned off my... Tell me if things sound different, everybody. Because I feel like I used to hear my between things. Maybe I'm just going crazy. Ah! I have no idea. Oh, computer audio. It says computer audio is off. Oh, I think I might not be. I have no idea. Let me look at my routing. No, I think everything's good. I don't know. Maybe I didn't used to hear that. There's no way for me to tell because I can't go back in time. Okay, let's get the exam up here. Brian is slowly losing his mind, but that's the way it always goes. That's how it is on Stat Tool 1. Little music right here. And let's get Canvas content going. Another version of the Canvas content. We're going to check out the Canvas content and see what we get. Canvas content. Let's go right here and check out Canvas content. And Canvas content at 2110. We're open questions after one more. We have one more of the women in a certain region question, and then we're free questions. So drop some questions in the chat. If you have more questions, here we go with Canvas content. Let's do it. This is a really good Canvas content. Make sure to use both your attempts and check it out because you're going to see me do a few here, but there's tons of different test questions, so make sure to check these out. A decision tree uses multiple X. True or false? Got an easy one here to start. Decision trees use multiple X's. We don't try to write too many trick questions, so you could be like, well, maybe. Should say a decision tree should use or is supposed to use multiple X's. I'm just trying to outthink the questions. Decision, very true. When you do a decision tree out here, you're going to input all your X's. The X's you do not input are going to be, that's the old notes. The X's you do not input are going to be ones that are categorical or identifier. Categoricals, that have too many levels. You want to use categoricals and quantitatives and multiple X's right here to explain one Y. So we'll be talking about this in the later class. If you haven't heard this, we'll use multiple X's to explain one Y. Key things right there. We always try to highlight those in the notes. So very true. A decision tree can use both. We got, Warren, we might do another version of this. We got like the easy one right here. We got some easy questions. A decision tree can use both categorical and quantitative variables. Warren, right here, what do you think? A decision tree can use both categorical and quantitative. Now, don't overthink it. It's just saying in general. Don't overthink it. We'll be very specific if there's issues on stuff like this. That's very true also. Yeah, decision trees use both categorical and quantitative. As you can see right here, usually like a lot of things we put on the test are usually directly from the notes. And then if I see things, I'm like, oh, I remember this is on the test. I remember try to highlight it. So you'll see me usually highlighting things that are the big things to know. If I see a slide that doesn't have things of major importance, I usually go a little quicker through it. And if I'm like, this is not a, like, I don't know. Not that some slides are not important, but not all slides are built equally. Some slides have more important. Response bias is always possible when we write questions as humans. Yeah, you can always. Response bias is when a surveyor or the question has bias in it that kind of pulls someone back from what the truth is. So when they have like a true response and we don't get it, and just by being humans, there's always response bias possible. The blank is a list of things or individuals from which the sample is drawn. Oh, this is the one I think Cassandra or someone was asking about. So we have the blank is a list or collection of things from which the sample is drawn. So is this a sample statistic, a sample frame, a population, or a sample size? A very good question. A very good question. I do like this question. Is it A, B, C, or D? Who would get this? This is a good question that I think would a lot of people would get wrong. Watch me get it wrong. So how is it, which one of these best describes it? You might be between two, but one of them is definitely a better choice. And don't worry if you get it wrong. We're going to just throw 100 points out there to start out, but don't worry if you get it wrong. Don't be like, oh no, just be like, this is practice. This is the practice. Warren, you got it right there. Warren is already saying the sample frame. The sample statistic is our estimate of a measurement of something about the population. It's the estimate of the population parameter. Like if I go out and ask people, are you in state? Then from 200 students, I find that 40% of them are in state. That's the sample statistic. The sample size is the 200 students I speak to. So sample size is the amount of people you talk to in your sample. The population is all people or things we are interested in understanding, where the sample frame, not the sample space, be very careful. The sample frame are the people or things we have access to talk to. So it's the things we could draw from. I wish it said access right there. One of those keywords I help people remember when remembering the term. but it's the list of things we can draw our sample from, so we have access to it. The sample space is the list of possible outcomes in probability. So oftentimes people get a little bit confused when they see sample frame versus sample space. Sample space, which we reviewed in some other videos, is the possible outcomes when it comes to probabilities. So that's what a sample space is. Sample frame is the possible things we could draw from in a population. Suppose the probability of a bus arriving on time for the next 5 stops is this. What is the probability that the bus is on time for at least one of the stops? Now, it does say assume each is independent, because what rule are we going to use right here? This is a tougher question, which can be solved very quickly. I'm not going to do the quick solve on it. Alexa's talking to me. She hears me at all moments. So why are we assuming independence? If we assume independence, we are about to use what rule? If we assume independence, we are about to use what rule? Be very careful that you understand, if we assume independence, we are asking, is it okay to use the this rule? So what rule are we about to probably use? I guess we could, I don't think we've ever written trick questions that say like assume this and then it doesn't use the rule. But it'd be a good indication if it says assume independence, we're probably about to go down the route of using a certain rule. And if you're assuming independence, it's the multiplication rule. So do remember this. Let's write this down right here. Oops, wrong side of the pen. Multiplication is going to have the word and it's going to have the independence rule, where addition uses the word or and has the rule disjoint, also known as mutually exclusive. So that is the very shorthand of what you're doing. So we are not using the addition rule, talking about or with things being disjoint of each other. We're using the multiplication rule, and we're saying the word and we're being independent. So independent means, which is an assumption of this problem, is that one outcome would not change the probability of another. So if we have a bus right here, here's our bus. We'll draw 5 bus stops. And with these 5 different bus stops right here, really? So with the 5 bus stops, we are asking, what is the probability that the bus is late at the first stop? It's not going to work. I failed at drawing, but the bus got longer somehow. Okay. What is the probability the bus is on time for at least one stop? So when these buses arrive right here, we could have that the bus is late, on time, on time, on time. So each of these are going to be independent. And we could say, what is the probability of this right here? So what we're asking is, at the first stop, it was late, and we'll put probability of late right here. Probability of late is equal to 45%, because probability of on time, we'll just call that T, is equal to 55. So the probability of it being on time is 55%, and the probability of it being late is 45%. So you could actually figure out the series of this event right here. How would we figure out it's late for the first, and then it's late for the second, and then it's on time for the third, and then it's on time for the fourth, and then it's on time for the fifth? Does anyone know how to figure out this probability right here? Like, how would you figure out the probability of this sequence? Now, this is not just the probability of it being late twice, but specifically the sequence, it's late for the first, and then it's late for the second, and then it's on time for the third, and then it's on time for the fourth, and then it's on time for the fifth. What would this mathematically equal to if you use these probabilities right here? So if we use these probabilities, what would this equal to? We've done questions like this on the test to say, what's the probability of them missing the first and making the second? Things like that, where you have to do a sequence like this, where you say, okay, this occurs, and then this. It wouldn't be 3/5, or well, maybe it'd be close to. So what we would do right here is we do 0.45 times 0.45, and thank you, Warren, 100 points following along right here, times 0.55 times, does this make sense what I'm doing right here? I'm just taking the associated probabilities up above. Does that make sense, Warren? I'll draw this on here so you can see. Those are the probabilities of it being on time. And you might be thinking of the final answer for this question. I haven't solved it for the final answer yet. But does that make sense right there, what I did to find that sequence of events? Cool. So the question asks, because now we can go to like the question if we understand like what we're talking about here, which is understanding the question itself is the first goal, and then figuring out what it wants is the second goal. It says, what is the probability the bus is on time for at least one stop? On time for at least one stop. What am I drawing out to you visually right here? Visually, I have drawn to you the probability of the bus is what for every stop. And I'll write it down here on the bottom. What have I drawn to you visually right there? What? And that's not the answer yet. What have I drawn to you? What have I drawn to you visually? What do we have visually right there? Visually, I've drawn to you via the color coding in the drawings. I've drawn to you the what? Visually, this looks like what right here? So the pink means it's late. So it's late to the first, late to the second, late to the third, late to the fourth, late to the fifth. So that would be the probability that the bus is always late. Does that make sense, Warren? This is the probability the bus is always late. Great job, Warren, right there. I'm on top chat, so I'm probably behind on time. Excellent answers, Warren. The bus is always late. So the bus is always late, or the bus is on time at least once. Does that make sense? So though one of those things must occur. Either the bus will always be late, or the bus will be on time at least once. One of these things must occur. Like it is either the case that the bus will always be late, or the bus will be on time at least once. That one of those things must be the case right here. It must be the case that one of these occurs. So these are disjoint events right here. We can add them. They're also complements because either the bus is late to every single stop or it's on time at least once. And that's probably the hardest thing for people to realize right here is how to write this down and to see either this will happen, it's always late, or it's on time at least once. Because now mathematically, we can just algebra this over to the other side. And once we algebra it over to the other side, now we can see why it's important we solve for this. Because if we figure out the probability the bus is always late, we can do 1 minus that to figure out it's on time at least once. So now we need to figure out the probability of this. Warren, what is the shorthand probability for what I'm about to write down right here? What is the shorthand probability for what I'm about to write down right here? Those are all 0.45s. So the bus is late all 5 times. What is the shorthand probability for that? Because then once we do this, we can get it, and we'll have it, and we'll be like, yay, we got it! We'll be like, I still love that sound effect. Yeah, exactly, Warren. Another 100 points. Great job, Warren, right there. And so that's going to get it. That's going to be the answer to the problem. And you might have watch it be. I think you might have found the answer or close to. So 2, 3, 4, 5. Oh, so it's very likely it'll be on time at least once. Was it probably on time? Good. I think so easy to make mistakes. This is probably we got lucky on so many of the problems, and then we got this one here at the end. So report your answer to 3 decimal place accuracies. Do not report as a percent. So wants it as a decimal. 3 decimal places. That should be right. Submit the quiz. We should get 100. 10 out of 10. There we go. Warren, hopefully that helped a lot. I don't know the concept of population is key. Yeah, oh yeah. Because we're trying to infer things about a population. So like the point of inferential statistics is to infer things about a population. So even though like statistics are about samples, the point of a statistic is to infer things about a population. Does that make sense? Like statistics are taken from samples, which are meant to infer things about populations. So the reason we have samples is to understand a population of interest. So a population would be key to understanding. Hopefully other questions didn't catch you, but that's so take a note on that. That's good for the test, right? So then on the test, when you see the concept of a population is key to inferential statistics, another Canvas content question right there. That is very true because statistics are estimates from samples, and samples are used to infer things about a population. Great work, Warren. If you got more questions, we could come back and do another example of this. Let's head back over to the main screen. Good stuff right there, everybody. Great work. Good practice. We got the adult women in a region. It's really good Canvas content right there. Last question was the difficult one. Some of them are tricky. Like you might see like a true false or something and be like, oh, psh, I got this. And you're like, what, wait, what? How did I, what? Oh no. It's a bummer. Okay, got the adult women in a region question. Okay, so let's go check. Ah, just made a mistake on my screen. Yeah, wrong screen. Oh, no. Wake up. Okay. What's the new timestamp? Okay, let's do this. Adult women in a region. Okay, so this is a sampling distribution question, and we're looking at right here what would happen if we took a sample of 400 women. The proportion of adult women in a certain geographical region is 49%, so we're just taking all people. I'm marking a survey telephones 400 random people, and so we have here, what proportion of the sample would you expect to be women? So this question seems more complicated because we use an equation, and let's take a look at what the equation shows. It looks super complicated if I write it this way. The question is asking what percent would you expect in a sample? So this says, what would you expect, because of the mu, that's like our expected, in a sample proportion? And the answer is the true proportion. And so now you might ask, well, what is P? Because P is the true proportion. So I expect to see the truth. It's like to say this. And so here's how it works. If 40% of UT is in state, if I take a sample of UT students, I'd expect to see 40%. If 80% of students love Taco Bell, that's the truth, then if I took a sample of students, I expect to see 80%. If 90% of people have seen the new Spider-Man movie and I take a sample of people, I'd expect to see 90%. So the right side is the truth for the population saying, well, this is true. So then in a sample, this is the sample part, I would expect to see this. It sounds more complicated than what we do, but it's as simple as, let's take the question. It says 49% of people in this region are female. So let's mark the notation so we understand how to do the notation on this, because it's going to help for later parts. But it says 49% are female. So 49% are female, that is P. That is the truth. And then it says, what do you expect to see in a sample? So now it's asking about P, mu P hat, mu P hat. What do you expect to see in a sample? The expect is the mu part of it, and then the sample is the P hat part, the sample proportion. So what sample proportion do we expect, the most likely? And frankly, as we said, well, mu P hat is equal to P. So the most likely amount to see, if 49 is true, well, if it's 49%, well, then the most likely amount is 49%. It just seems complicated when we put numbers to it, but conceptually, if I say 49% of people are female, you take a sample, what percent of females do you expect to see in the sample? You're like, well, 49% of people are female. I'd expect to see 49%. Seems complicated, but it's not, I promise. Standard deviation is not too complicated either if we know the notation for this. The notation for the standard deviation, and great work, everybody. And it's like once you see, you're like, oh, that's all it's asking. Now, if we know the notation, this one will get a lot easier because it's P times Q over N square root. So now we got to ask, what is Q? Well, P is the true proportion. So whatever it says is the truth is P, and Q is the complement of the true proportion. The complement means it adds up to 1. So review from probability. So it says if 49% is P, Q is 51% because they add up to 1. P and Q add up to 1. Double check your math. And if you want to ensure, go ahead and do 1 minus P, and you will get Q right there. So just remember P and Q add up to 1. P and Q are complements of each other. They add up to 1. And so now we need the sample size. So the sample size is going to be over here, which is the just amount we spoke to. And you'll notice right here, this is N. So we're just going to plug into the equation. We'll disappear here for a moment. And so we're going to plug P. Got another question? Yeah, the bus question. 4 stops. But that's, you might have found next 4 stops. Be on time. Okay, Warren, let me look. Great job, Warren. Let me take a look at the next question. Let me look at that. We'll take a look here in a second, Warren. Thank you so much. There we go. Let's find out. We'll find out what happened there. I think you might. It looks like it's missing a 1 minus. And then we'll see, Warren. We'll take a look. There we go. There's the standard deviation. 3 decimals. Check answer. Ooh. How many women on average would you expect to see to find? How many women on average would you expect to find in a sample of this size? So if we expect 49%, so we expect 49% women out of 400. So it should be 196. And do we have more? That's got it. That's just how many we would expect. Well, Warren, we'll take a look right here and see what the issue is. Let's go take a look at that question. Let's see. I had the bus question. Let me take this. Chemos content. Let's take a look. Okay. Let's take it. Ah. Okay, bus question review. Canvas content. Bus question review. Let's go check it out. Here we go. Okay, so I had the bus arriving on time is 50%. Okay. So the bus arrives on time 50% of the time. And that's the probability of on time is equal to 50%. And the probability of late is the complement. It's either on time or it's late. And then you want right here, probability on time, be on time at least once. I think it's at least once, right? Because it's usually at least once. Be on time at least once. I'm pretty sure it's at least once, right? Warren, correct me if I'm wrong on this, but I'm pretty sure on time at least once. Oh, no worries, no worries. 100 points. Don't worry about it. Don't worry about it. All right. So we want the probability it's on time at least once. So when we write this, we always want to write this out that either the bus is always late or on time at least once. So here's our equation we're writing out. Either the bus is always late or the bus is local news area. Yeah, definitely. Either the bus is always late or on time at least once. So let me take the note out here. Either the bus is always late or it's on time at least once. Local papa. So with this right here, we want to find out the probability it's on time at least once. Let's change this mathematically. And we're going to write right here a plus because that's what we do when we say or, because these are disjoint complements, so we can add them. And so then we want to figure out, we're going to subtract this from the other side. We're going to do a little algebra. And then we want to figure out the probability it's always late, because we're just algebraing that over to the other side, because this is the one we're interested in. So what's the probability it's always late, Warren? So what would be the probability the bus is always late? And I think I see the issue. What's the probability it's always late? So it has to be late to the first stop, late to the second, late to the third, and late to the fourth. So it needs to be late and late and late and late. Exactly. And so I think this is where the issue occurred, because the probability of always late, we did a longer solve of this earlier, check it out. And so Warren, I think I see the issue because I see the answer you got, and then you forgot one thing, because this, I think right here is what you were getting. Do you see the issue, Warren? And good work. It's a small mistake to make, and a lot of people make it on the test. So 1, 2, 3, 4. So now what do we have that we need to do? I think you'll see it. So that's the probability it's always late, but we don't want that it's always late. We want the probability that it's not always late, because it's the complement of always late. So do you see it, Warren? I think you're right there to be like, I just one step. It's great job, Warren. There you go, 100 points. Yep, very common error, and then that will be the probability right here. So this is the probability we are looking for. Just 1 minus that, because it's either always late or not always late, and very common small thing. But Warren, great work and good practice. And then just practice writing it down like this to see it and to understand what you're computing, to be like, I want the probability that it's always late. So it's late for the first, late for the second, late for the third, late for the fourth. And check out the longer solve of this. If people want, where we did the longer solve right here, going through and different numbers and stuff. But good question, good practice. Warren, don't say sorry. Warren, 500 points. Don't worry. We're here to practice. Warren, I appreciate, you know how many people during class today, I think you're in the morning class because we were talking at the end, I believe, unless it was another Warren, but people were saying how much office hours help. And Warren, you're part of that reason. If you're here asking the questions, because this is a tougher question. This is one of those ones that people get to on the test. Some people just say, I don't know. They say, I don't know how to do this. And I don't want to, I was just like, I'm like, no, I'm like, let's practice it. Let's get it down. And then it's still tough, but the more you practice it, the easier it gets. Still easy to make mistakes though. So Warren, you got this. Great work right there. You got this, man. And so we're going to do the newspaper question, which is also a tough one. Ooh, doing all the tough questions today. Listening to some chill music. Brian has the sniffles. Brian's all sad today. I'm not sad. Newspaper referendum question. We're in a lot of good work done today. We have no more questions after this, so drop them in the chat. I'll fall asleep. Here we go. Newspaper question. Let's do it. Here we are with the newspaper question. And this question is a tough one for just one number. We have to find one number, but it's a lot of work. So if you've watched the other examples we were just doing, there's two things we need to know for a distribution. The two things we need to know for a distribution are going to be the mean and the standard deviation. So anytime you get a problem, you'll want to know the mean of it, the center. The first number is the mean, and the second number is the standard deviation. So let's go ahead and start doing that for this problem and know what we need to know. To find the mean of a distribution of the sample proportion is going to be mu p hat, which is the expected, mu stands for expected, sample proportion, what we expect to see in a sample is equal to the truth. Whatever the true is, like 80% of students like Taco Bell. Well, if I go ahead and sample students, I'd expect to see 80% of them liking Taco Bell, if that's the truth. The next thing we need to do is find the standard deviation, because that's going to tell us how spread out it is. And we would find that that is P times Q over N square root. So now you might be asking, what are P, what are Q, what are N? And then let's solve. Well, N is the simple one. That's the sample size. Just how many people did we speak to? So that's the really, really easy one. Next, we have what is P. P is the truth. So whatever the truth is what we know to be true about the population. So it is true that 55% of people will vote for this. 55% of people is the true proportion, and so that is equal to 55%. And the complement of this is Q. Q is just going to be 1 minus it. So Q is equal to 0.45. So that is the complement of the truth right here. Very important to know P, Q, and N. Usually people remember N because it's sample size. We use it a lot in all equations. But P and Q, P being the true proportion, is true that 55% of people will vote for this. Q is, it is true that 45% will not vote for it. So now we have this. The question asks, what is the probability that the newspaper sample will lead to predicting defeat? So that means, so we could say, what is the probability? What is the probability in a sample we see less than 50% voting for this? Because if we see less than 50% vote for it in the sample, we will predict it leading to defeat. And that's usually where people get stuck. It's like, well, what are we solving for? We're trying to see less than 50% vote for it in the sample, because we're going to predict defeat to say, oh, well, we did a sample of 432 and less than 50% said they'd vote for it, so we predict it'll be defeated. But what is the most likely percent? So take a moment right here, give it a good 10 seconds. What is the most likely thing for us to see in a sample? The most likely thing for us to see in a sample would be what? So the most likely thing, if we go out and sample these people, the most likely percent to see would be what? And the answer is up top. The most likely thing to see in a sample would be what? The most likely thing to see in a sample would be what? Because it's the truth. The most likely thing to see in a sample would be P, because that's what we expect to see. If we know the truth for some reason, we know it. Some reason in this example, we know the truth, so the most likely thing to see in the example would be the mean, and that's the truth, and that's here at the center. Next, we need the standard deviation to draw this to tell us the variation around the truth. And that's going to be when we go up 1, 2, 3 standard deviations. And the down is going to be more important right here to say what could happen in a sample, the variation we see. And so let's draw our 3 standard deviations on the curve. Not perfectly symmetric, but it'll do. Go a little bit in on this one. Got to make it look really good right there. We're drawing some A+ drawings today. So now we need to find P times Q over N square root. Let's go ahead and solve this. Remember, P is the truth. 55% are going to vote for it. Q is the complement, 1 minus it. So those add up to 1. Divide by the sample size, P times Q over N square root of the whole thing. And now we get basically 0.024. And that is the standard deviation. I'm going to round it. I don't think the problem is going to get mad at me. That's good enough. And now if you notice, we need to go down standard deviations. We can kind of estimate this. Let's go minus a standard deviation here, 0.55. Nope. 0.55 minus the standard deviation is 0.526. That's minus 1 standard deviation. We're going down another one. And the reason we're doing this, you might be wondering, well, why are you doing this? I want to see about where 50% is at. And this will help me kind of guess the answer. Like it's a test question where I have to guess the answer. So now you notice, this is why I like this question right here, right now, that less than 50% occurring is very close to a z-score of -2. Z-scores are how many standard deviations we are above or below the mean. So it's kind of close to a z-score of -2. Because of this, and it's very close to it, I can probably take a good educated guess at this answer. It says to 3 decimals, so I'm going to guess a little bit less than 2.5%, and then we're going to see it via the applet. So once again, I'm guessing this based on my drawing. If I get this right, it's because I did a really good drawing, and then I was able to guesstimate it. So let's check the answer. We did get it correct, and that's thanks to the drawing right there. Remember the empirical rule. I'm going to show the empirical rule on here real briefly. The empirical rule would state that between, let's do a different color. We'll go to orange for UT. Between here and here is 95%. And then outside of here, specifically here, is 2.5%. And because of that, I guessed a little bit less than 2.5. So that was a guess. You might not be able to guess it as accurately, but on the test, we could put answers like 2%, 4%, 5%. And if you know it has to be less than 2.5, you would narrow it down to that answer. That's how we can do a multiple choice on the test. You could have responses like 2%, 3%, 4%, 5%. And then a lot of people might think, these are the right ones because they're in the middle. But logically, the answer could only be this one, and it rounds very close to 2% because it has to be less than 2.5%. It has to be less than 2.5 because of the empirical rule. And that's how we could do it on a test. Because a lot of times, well, how would you do this on a test? Well, you could draw it out and then take a good educated guess at it. But let's go over to the David M. Lane because your problem might not have such nice, neat numbers on it. So on your assignment right here, use the David M. Lane. And let's go to the David M. Lane. And we will enter in the mean and the standard deviation. The mean was the center of the curve. And the standard deviation, I just still have it in here. And now below, and your drawing should look like this. And I want you to see something. Can we get it on the screen at the same time? If you take a look at what we have on the screen right here, in both spots, it should look very similar. And this is when you know you've done your drawing right. This area right here, which is what I was looking for. So specifically, before I did all this with the empirical rule, we're trying to solve for this area right here. That's what we're interested in. And then we did this big drawing right here, and we got the following. And you want to see that what you have looks very similar. And it was actually even less than 2%. I got kind of lucky on how it answered it. But your drawing should look like that. So practice drawing it out. If you can draw it out, you'll probably be pretty good on understanding and communicating the ideas. But that's got it right there. That's our drawing, the probability of less than 50%. And Cassandra did that help out. Hopefully it made sense. I think we've almost done all the questions on this homework. We've only got 2 more, so let's finish off the homework right here because we've done most, if not all, the questions. So we'll see question 1, and then we'll come back to this. Let's do question 1, fundraising dinner, Hello, Teresita. Good to see you here. Put questions in the chat if you got them. Let me know. We're going to do the fundraising dinner because we see it. So let's do the fundraising dinner, but drop questions if you have them in the chat. I'm just kind of finding new questions. 55. Okay, let's go check out fundraising dinner. Here we go. So this is a theory question on what happens to the sampling distribution of the sample proportion. When we have the sampling distribution of the sample proportion, the equations for it are, and we've seen it in previous questions, the mean of the distribution is equal to P. So we're just going to write only the equations from the previous question. And P is the truth, as in we know 55% of people in this previous question are going to vote for the referendum. The standard deviation of the distribution is equal to P times Q over N square root. So with this is actually going to help us right here because only one of these deals with the sample size. The sample size, when you look at the equation for the center, and let's label this, this is the center right here. The center is that, and the spread is this, because it's standard deviation for spread. The center, Rock knows, the sample size, Rock, where are you at?
It doesn't matter.
The sample size is not going to matter right here. So if you notice, there is no sample size in this equation for the center. So when we figure out the center of the distribution, as the sample size increases, the center stays about the same. It should just say doesn't change. The shape of the distribution is actually going to become more normal. This is a very important thing right here because if we have a large enough sample size, it will be normal. And I'll show this conceptually right here. 2 seconds right here. Let's bring up the conceptual. So this is the central limit theorem. Binomial applet Iowa right here. So as the sample size increases, it becomes more normal. And we'll go here, 2 seconds, 10, cool. We'll go very small on this. There we go. Here we are with the sample size of 2 with it not being normal. As I increase my sample size to things like 5, it still looks not normal. 10. Let's go here to 16, why not? Now let's go to 30. Let's go here to 50 and look at it. It's starting to become more normal. 200, very normal shape. The condition is we need at least 10 successes, at least 10 failures. So if you don't have at least 10 successes, at least 10 failures, it won't look normal enough. So as the sample size increases, it starts to become more normal because you have the possibility to have at least 10 successes, at least 10 failures. This is known as the success failure condition. Like the problem doesn't go into enough detail on this, but it is true that if we have a larger sample size, the distribution will start to look more normal. And you're starting to see it here with my example of me increasing the sample size, it becoming more normal, decreasing the sample size, not normal. So theoretically, and this is a good theory question, as the sample size increases, the shape of the distribution will become more normal. And the variability, if you notice in the equation for the variability, which is the spread right there, it'll decrease. So the spread is P times Q over N square root. So the sample size, which is N right there, as the sample size increases, the variability will decrease. So theoretically, the variability in the sample proportion decreases, and we see that mathematically. We don't even need to look at the simulations because the simulation, all simulations that are properly done, which we would assume this one is, will show this. They do appear to show this. And we could take a look to see this. Small sample size, not normally distributed. Larger sample size, more normally distributed. Center of distribution around 0.9 something. Center of distribution around 0.9 something. So the center stays about where it's at. Spread of the distribution will actually get smaller. And that's best noted right here that this goes from 0.75 to 1. And at the end right here, it's not even spreading all the way to 0.85. It's starting to narrow in on it. As the sample size increases, it'll become more narrow. So definitely what we would expect to see that the distribution gets a lot closer, smaller standard deviation. The distribution gets more normal, as we see right here. Not normal, more spread out, less spread out. And also the mean, which is harder to see, stays about the same. But theoretically, it's easy to see right here that the mean of the distribution is P. That would not change with the sample size changing at all. The sample size only impacts the shape of the distribution, becomes more normal as sample size increases, and the sample size would also impact the standard deviation, and the formula can help you see that. That's a really good question. Check those answers. Good job. Let's head back. We only have one more from the homework, the nearsightedness. Let's go check it out. We'll have completed all the homework. Good homework stuff right here. So let's get the nearsightedness on the homework, which I am very nearsighted. I was like, I can't read anything. If you have questions in chat, let me know. Disconnect, reconnect. Come on. We're on a streak right there. First one of the day. Well, Leo. Sigh. So, nearsighted. Let's go check it out. Here we go. This is the nearsightedness in children problem, which is going to first ask us about the conditions. Now, condition 1 is random. Did we randomly select these children? We'd kind of have to assume that random selection is the first condition. Condition 2 is less than 10%, which is, a lot of people don't understand, is less than 10%. It's a very interesting mathematical one where you have to take less than 10% of the population or you've oversampled. There's a lot of theory, and there was such a good site on the internet that went into such great detail, and it went away. It was probably like some instructor's site, and they took it down. But yes, sad day for us. On kindergarten, and then the last condition is at least 10 successes, at least 10 failure, known as the success failure condition, NPNQ. So let's take our notation down here to help us with the later parts of the question, and we could also see the NPNQ condition is met. So anytime you get a question like this, you need to write down the notation. So we always try to practice our notation to understand that P is the true proportion, Q is the complement, is equal to 1 minus P, and N is the sample size. So P is the true proportion. We've sampled 13% are expected to be nearsighted. 87% would be expected to not be nearsighted, and we are taking a sample of 178. From this, we can then solve the equations, mu p hat, which is how many we'd expect to see in our sample to be nearsighted, and then we could get the standard deviation, which is the variation in what we'd expect to see in our sample. Like, we won't always see this. We might see variation around it. Like, if I tell you 13% of children are nearsighted and you take a sample, it's probably not you'll see exactly 13% in every sample. You'll see maybe 13%, 14%, 12%. It's probably unlikely you'll see like 80% of students are nearsighted. Very unlikely. So P times Q over N square root. And here we go right here. So 13% times 87% over 178. And we'll find that. This is just 13%. And almost forgot my square root. Let's solve that out. And P times Q over N square root. About 1%. Ooh, makes it nice and easy right there. Oh, that's really close to it. So 0.0108. And that's got that right there. Now we need to draw out the distribution. So with this, we'd take our distribution, and I'm just going to round it because this is a really nice one. I'll use David and Elaine to get the exact answer. But this is 13%. Or we'll just do it as percentages because I can just write it a lot quicker if I go 13, 12, 11, 10. And these are roundeds because the standard deviation is about 1%. It's going to give me a good estimate right here, and we'll use this in a moment. Assume these are typical. Sounds good right there. And now look here. We have our distribution that we were trying to draw out. It's giving us the numbers also, but we see right here that we were at 13%. Oh, we have a problem. I didn't do the standard deviation correctly. It looks like the standard deviation is closer to about 2%. Let's resolve that standard deviation because something went wrong. P times Q over N must have, oh, that's, yep, there it is. So it's 2.5%. So if you notice, you would go down 3 times to get to this. If you go 13% minus 1 standard deviation, 2 standard deviations, 3 standard deviations, you're getting this number right here rounded. 13%, which is at the center of the curve, plus 3 standard deviations. There's a standard deviation. and there are 3 standard deviations. That's the upper number on the curve, and they didn't even round it properly, but that would be the curve right there. So just make sure, don't make a math error like me. It's easy to make. So the last question asks, well, how many children would this be? Remember, we are sampling from 178, so we'd expect between 5.5%. So from 178, we'd expect around somewhere as low as 5.5% according to the curve. So that would be 10. And then the next number we should get, we'd expect as high as, out of the 178, this many, and that would be the number 36. And that should do it. And yeah, we've done all the homework. Might end a little bit early, but what questions are there? So we've done the whole chapter 13 homework. We've done Canvas content today. Good stuff. Let me know, what questions are there? We've done all of chapter 13. We've done the Canvas content, multiple versions of Canvas content. What questions do you have? Let me know. I think office hours go to 1 anyways, but usually we go over. We relax. Might answer some emails. See what Discord's up to. Grab some lunch. Oh my gosh. A novel concept, eat lunch. I should call Kroger for flowers for wedding. If you have questions, let me know. We hang out a little bit longer, as you know, but I think we might head off for a little bit. But join into office hours anytime and ask those questions. But we got all of chapter 13 done. Good review of the problems, good practice. And I guess I don't see any questions in the chat. Unless we're at 100 points. I'm going to grab some lunch and make some calls. See you all. Brandon, great to see you here. Thank you so much, Brandon. We'll be back. I'm going to head off for a little bit, grab some lunch. Bye for now, everyone. Bye. Eat some lunch. Enjoy.